let's try to finish it today. We talked about cache. We are in the memory hierarchy. We talked about cache, direct map cache, and the last thing we covered, I believe, was talking about the spatial locality and the type of cache that bring more words from the cache, from the main memory to cache every time that we go to the cache, and how much this spatial locality can help us to increase the hit rate. Okay, so this is where we stopped, and now I want to talk about, I'm going to go a little bit deeper, and I'm going to talk about the types of cache misses and different types of caches that we have. So we have 3 types of miss in the cache. And just as a reminder, when we have a miss, it means that we go to the cache, the data that we want to work with is not in the cache, so we have to go to the main memory and bring it to the cache. Okay, that's a cache miss. The first reason that we can get a cache miss is compulsory miss. This usually happens at the beginning of the program. You don't really have any data in the cache. In other words, the valid bit is not valid. So when you go there, the data is not in the cache, and the data is not valid, so we get compulsory miss. This is not that major, because compared to how many memory accesses we're going to have during the program, this is kind of negligible. But there are solutions to fix this problem too, and it is called prefetching. So prefetching means we bring a part of the memory, we bring a block to the cache even before running the program. Right? So you can do some prefetching, and that helps with some of the compulsory misses. Okay? But there should be a smart way of prefetching depending on the application. We don't want to go there, but that's one way of fixing this compulsory miss. The second type of miss that we can get is the capacity miss. Right? So we already know that cache is smaller than main memory. That's the whole point of it. And because we don't have enough space in the cache, because of the capacity limitations, we get some miss. And how can we fix it? We can make the cache bigger, but it's always a trade-off, right? You don't want to make it too big, such that the access time is so long, and you don't want it to be so small that you get a lot of capacity miss. Okay? The third type of the cache miss is the conflict miss. And this is when we have like a kind of cache strategy like direct mapped. So we mentioned in the direct map, there are many different blocks in the main memory that are mapped to a specific line in the cache, right? So in case of the conflict miss, this happens when you have 2 different addresses, they're mapped to the same location in the main memory, and then there's a conflict. Right? So how can we fix it? We can increase the size of the cache. That reduces it, but again, there's a trade-off. There is another way that is called associativity that we're going to talk about today. That is going to help with this kind of conflict miss. We're going to see how. So now let's have an example of the conflict miss and see how it works and how it can cause problem for us in the program. So we have these memory addresses, that, as you can see here. And then we have a cache size of 4 words, and we have 4-bit memory address, so it means A is equal to 4, if you don't remember. And then we have 1 word per block and 1 byte per word. Because we have 1 byte per word, it means that we don't need any bits to address the byte in the word. Because we have 1 word per block, it means that we don't need any lines to address the word, different words in the block. There's only 1 word in the block anyways. So what it means is that W is equal to 0. If you don't remember the direct map encoding, I'm reminding you. W is equal to 0, M is equal to 0, A is equal to 4. And then what's the cache size? We have a cache size of 4 words. It means that we have 4 lines, and we need 2 bits to address these 4 different places in the cache. So it means that N is equal to 2. Which means tag will be equal to 2 as well, because A is equal to 4, right? We just did a bit field encoding right here. So now let's see how it works. The first value that we want to get is from address 0. So address 0, if you look at the line, these 2 bits are going to be the index for the line. So we're going to go to line 0, but because there's nothing in the cache, we're going to get a miss, right? So what kind of miss is this? Compulsory miss, right? This is a compulsory miss because we don't have valid data in the cache. The tag here would be 0, 0, and the content of the memory would be whatever is in the memory address 0. Now we go to the next line, we have 4. Looking at the 4, 4 has the index of 0, 0 again. It means that we're looking at the line 0. So now this time when we look at the line 0, we don't get a compulsory miss because there is something in the cache, but the valid bit is 1, right? But what is that something? Is it the value that we're looking for or not? To find that, we have to check the tag. When we look at the tag for this address 4 is 0, 1, right? Which means that this is going to be a miss because the tags are not equal. But this one is not a compulsory miss. This is a conflict miss. Why it is not a capacity miss? Because we still have a lot of space in the cache that we're not using as a conflict, as a conflict miss. Now we have 4. Replace that value with 4. Now the new tag is 0, 1. The address is memory 4. The next address is 0. You can see where I'm going with that, right? 0 is going to be the first line again. The tag is not equal. It's a miss. It's a conflict miss. Then we have 12. The new value is going to be 0. 12 pointing to the same line. The tag is not equal. Tag is 1, 1. It's another miss, right? Conflict miss. Now the new value would be 12. 8. Same line, different tag, miss, right? And so on. So this is how we get all this conflict miss because of these addresses. The problem here is not because we don't have enough capacity. The problem here is because of the way it's mapped to that location. All these addresses are mapped to the same location in the cache, and that is causing conflict miss. Sorry. Okay. So we have 8 requests, 8 misses. Hit rate is equal to 0. Still, we have a lot of capacity. That is the problem with the conflict miss. Okay. So now, let's see how we can fix this problem with associativity. So, the whole idea of that associativity is that they want to give it more flexibility. In the direct map cache, every memory block is mapped to one location in the cache, right? As fixed, no flexibility. Okay. Another alternative is we give this option to the cache that every block in the main memory can be mapped to a different location in the cache. Right? This is called fully associative cache. The other side of the spectrum. So every block in the main memory can be mapped to any block, any lines in the cache. This is the fully associative cache. But we have something in between, which is k-way associative cache. The k-way associative set associative cache, we have different sets in the cache. You do have flexibility within the set. So different locations in the memory are mapped to same sets. That's correct, right? This part is like direct map. But then instead of mapping them to an exact line in the cache, we map them to a set. But within the set, we have k number of ways that we can map different locations in the main memory to the cache, right? So we have k lines in each set, and we have a specific number of sets in the cache, okay? And within the set, we have flexibility. So this is something between direct map cache and fully associative cache, okay? So now let's talk about the fully associative cache first. Let's talk about the encoder. The fully associative cache, as I mentioned, every line in the main memory can be mapped to every line in the cache. Every block in the main memory can be mapped to every line in the cache. So basically, we don't have the field that gives us the address to the lines in the cache. So if you remember, we had a field n in a direct map cache, and what n was doing was giving us the address to the line, to that specific line in the cache. Right now we don't have such a thing because every line in the block can be mapped to every block in the main memory can be mapped to every line in the cache. So we don't really have addressing there. We don't have to address different cache lines that way, okay? But we still have bytes, remember. We are working with the byte addressable memory. So we still need to look for bytes inside the words, and we need to look for words inside the lines after finding the line. So we find the line, and then we find the word inside the line, then we find the byte inside the word, okay? For that reason, we still have the fields W and M. So W is addressing the bytes in the word, M is addressing the words in the block or in the line, and everything that is left is tag. Tag is providing the address to the line. Okay, so we have a pretty big tag because of the flexibility that we can get. Alright, so now let's have this example of a fully associative cache. So we have a MIPS-based tablet that has 4 gigabytes of main memory, and it has a single level of fully associative mapped cache. Single level means we just have one layer of cache. Fully associative mapped cache, and the block size of 32 words. Okay, so what is the bit field encoding for memory addresses? So we have fully associative cache. It means that the fields that we have to look for are the field W, M, and tag, whatever it is left. Okay, to find W, we have to see how many bytes we have in each word. Right? So it's a MIPS-based processor. How many bytes do we have in each word in the MIPS-based processor? We have 4. That we know. This is the information that I don't give to you. If it's something else, I'll let you know. But if you say MIPS, you're supposed to know that MIPS has 4 bytes in each word. Okay? So it means that W would be 2. Okay? 2 to the W is equal to 4. W would be equal to 2. So we need 2 bits to address the words, address the bytes inside the word. The next thing we want to look at is M. And M is about how many bits we need to address the words in the block. So if you look at here, it says that we have a block size of 32 words, which gives me M equal to what? So we have 32 words, and that's right, yeah. We need 5. So we have 32 words in each blocks. It means that we need 5 bits to address each word in the block. Right? But how do we find the address for the line in the cache? For that, we have to find the tag size, right? So tag is going to give me the address to the line in the cache. But before finding the tag, we have to find how big is the address bus, because whatever is left is for the tag. So to find how big the address bus is, we have to find the memory capacity first. So memory capacity is 4 gigabytes. It means that I have 2 to the 32 bytes, which makes A equal to 32, meaning that I need 32 bits to address each byte in the memory. So A would be 32. Now I have A equal to 32, M equal to 5, and W equal to 2. It gives me a tag size of 25. Okay, so if I do the bit field encoding, this is what you're going to get. You need 2 bits for the byte field, you need 5 bits for the word field, and we have 25 bits for the tag field. Okay? Does that make sense? If you're having trouble with these conversions of 2, 5, and A and whatever we're doing here, we covered that in the last 2 sessions, so you can watch the video of that and see how we do it. Okay, so now let's have an example of a fully associative cache. And sequence of addresses that they want to access in the memory. Let's see how fully associative cache handles it. Okay, so we have a cache size of 4 words, 4 bits memory address, so A is equal to 4. Then we have 1 word per block and 1 byte per word. It means that W is equal to 0, M is equal to 0, tag would be equal to 4, right? So the entire memory address is used for tag. You have 4 bits, all of it is used for tag, okay? So now we have the first memory address, 0. It's a miss. What type of miss it is? Compulsory miss. So now we bring the content of memory address 0, but the tag would be the entire address, 0, 0, 0, 0. Okay, the next one is 4. 4 is another compulsory miss that we have here. But what is going to happen here is that 4 is going to sit in the next place in the memory, because it's a fully associative cache, and tag can be used to address that block. So this is going to be 0, 1, 0, 0, which is the tag, and then we have the content of memory address 4 inside the cache. Now next time we have a 0, if we didn't have fully associative cache, we already knew that here we're going to have a conflict miss. In the case of direct map cache, we had a conflict miss here. But we're not going to have a conflict miss here because 0 is already in the cache. Okay, so this is going to be a hit. When we have 12, 12 is going to be another compulsory miss. And now we're going to have the content of memory address 12 in the cache as well. The next memory address is 8. It's a compulsory miss. And 8 is going to sit here. Okay. After that point, we have a hit of 4. We have another hit. We have another hit. Okay. The same memory accesses that would have given us 0% hit rate in a direct map cache is giving us 50% hit rate in a fully associative cache. Okay, right here we see the benefit of having a fully associative cache. So, there is a very interesting question that you can ask right here. So I'm going to ask you, do you know what that good question is?
Well, we use this all the time.
What? No. that's a funny question. Why don't we use fully associative cache? But like, what is a good question here?
If you add a decimal that's not currently.
So what if we have a new address which is not here and the cache is full? Okay. In a direct map cache, basically we're talking about the replacement policy. In a direct map cache, we already know what a replacement policy is. When the 4 comes in, we know where it is located, when it should be located. It's going to be mapped to that place, and it's going to just replace the content of that value. What if we have 9 here in the next memory address? What is the replacement policy here? Okay, that's a good question, which I'm not going to answer right now. You have to wait for it for another 20 minutes. But that could have been a good question, right? What is the policy here to replace this number? But before that, let's talk about the k-way set associated cache. We're talking about fully associated cache, and I want to talk about the k-way set associated cache. One of the reasons, let me answer Adam's question. So why don't we always use fully associative cache? Because if you look at it, if we have a really big cache, it's going to take a long time to address this. So the memory accesses are going to be longer, right? This is kind of like a memory by itself. Like we have a big tag, we have to search within the cache. Like we don't have this hierarchical path to find the location. Like they had a huge tag, access time can be longer. Okay? It costs them overheads. So now the trade-off here is using a k-way set associative cache. In the k-way set associative cache, we have an extra field called S. S is for addressing the specific set in the k-way associative cache. So we mentioned that different locations in the k-way set associative cache, different locations in the memory are mapped to a set. This part is like a direct map cache, but within the set, you have k lines. those lines within the set don't need an address because you have full flexibility within the set. So this part is like a fully associative. So you don't need a field to find the lines, address the lines inside the set. But you do need a field to find the set because every location in the main memory is mapped to a specific set, not to a specific line. A set that only has one line is kind of like fully associative anyways, or relative. Okay, so we have a field of S here, and now we'll take it from here. So let's have this example. We have an embedded 8-bit microcontroller that has 16 bytes of main memory, a two-way set associative map cache containing 4 lines, and a block size of 1 word. So let's do the bit field encoding for this. Information here is we have a two-way set associative map cache. So this is how we know what the cache is, the kind of question that you can get in the exam too. So step by step, the first thing we want to do is we want to find how big the address bus is. Right? What is A basically here? We have 16 bytes of main memory, which means we have 2 to the 4 bytes. It's byte addressable. A will be 4. Okay, A is equal to 4 because we have 16 bytes of main memory. Next step is how many bytes we have in each port. I mean, first of all, this doesn't have an order, right? I'm just telling you can just find any of these independently, so you don't have to stick with this order. But like how many bits, how many bytes do I have in each port? This is the part that you need to know when I say an 8-bit microcontroller. This is talking about the word size. When you have a 64-bit processor, it means the word size is 64. When you have a 32-bit processor, it means the word size has 32 bits, right? You are familiar with that on your computers that you're using. You have 32-bit, 64. That's the word size. So when I say an 8-bit microcontroller, which actually do exist, by the way, it means that my word size is 8 bits, is equal to 8 bits. And 8 bits is 1 byte, so every word is equal to 1 byte, which means that W would be 0. We have 1 byte per word. Okay, so the next thing we want to look at is M. So how many words do we have in each block? Okay, so this information is also provided here already. We have block size of 1 word, 2 to them is equal to 1, and would be equal to 0. So now, the last thing that is important for us, because it's a two-way set associative map cache, is finding how many sets we have in the cache. Okay, so we have a field for set. We want to see how many sets we have in the cache. So how can we find it? We have this information about the cache that it has 4 lines. So our cache has a total of 4 lines. We also know that this is a two-way set associated mapped cache. So two-way means that I have 2 lines in each set. So each set has 2 lines, and we have a total of 4 lines in the cache. So it means how many sets we have here? We have 2 sets. 2 lines per set, 4 lines in total. It means that we have 2 sets in the cache. If we had 8 lines here, we would have had 4 sets, right? And so on. So we have 2 lines in the set, and we have 2 sets in the cache. So it means that S will be equal to 1. Right? We have 2 sets. 2 to the S is equal to 2, which means S is equal to 1. So if I do the bit field encoding for this, we know that the tag, whatever is left as tag, we have A equal to 4, WM is equal to 0, S is equal to 1, T would be equal to 3. If I do bit field encoding, this would be 3, 0, 0, 1, and 3. Right? We don't even show M and W here. Okay? Now let's see how a set associative cache works. Okay, we have an example of like this, 04040404. This would definitely lead to conflict miss, this ping pong effect, and would have a hit rate of 0 if we had a direct map cache. Okay, so now let's see how a set associative cache works. So this memory information is exactly the same thing that we had in the previous slide. We already did the calculation, and we know that we have 0 bits for byte, 0 bits for word, 1 bit for set, and 3 bits for tag. Okay? So now we have the first address. It means that we have to check this bit, the first bit, and that is telling me whether I should look at set 0 or set 1. Right? So here I'm going to have a compulsory miss anyways because there's nothing in the cache. So now we have a miss, but the 0 is going to sit in set 0. Within this set, we do have flexibility. It can sit anywhere in the set. The tag has 3 bits, we're going to have 0, 0, 0 here. The next one is a 4. So 4 is another compulsory miss because we don't have the data there. And we come and sit here. But we look at this 0. This is for set 0. So we look at set 0. But when we check the tag, see that this doesn't exist in the cache. So 4 is going to sit in the second line in that set. After that point, we're going to have this, right? So if we have 8 requests and we have 2 misses, and those are both compulsory misses. Okay? Does that make sense? So now, let's talk about the good question that I said you can ask. The replacement policy. So replacement policy is basically answering this question. What happens when the cache is full? Basically, what happens when we have capacity miss? Okay, we have new data coming in, the cache is already full, what do we want to do now? Right? In the case of a direct map cache, you don't even have a replacement policy because every plug in the main memory is connected to a line in the cache. It's mapped to a specific line in the cache. So there is no replacement policy. The data comes there, it's either exist or no, it's going to be replaced, right? No policies here. But this can cause some issues. So besides the conflict miss that we talked about, this doesn't have any policies to value the temporal locality that we talked about. So there is a high chance that you bring a data in the previous clock, and then you go and bring the next data, and it's going to be replaced by the most recent one. The temporal locality was telling us that if you bring a data, give it some time, then there is a high probability that we're going to use it again. Direct map is not valuing that temporal locality, principle. In a fully associative cache, or set associative cache, we need to decide which one we want to replace because of the flexibility. When it is full, there is no direct policy which one of the data that we have there is going to be replaced. Okay, so we need to come up with policies for replacement. Okay, so I talk about 2 important policies. One is the least recently used policy. So we just check and see which one of these, the data that we have, which one of these memory addresses is the least recently used one. So this is valuing the temporal locality. Right, and the least recently used is going to be replaced. If I access that memory address 20 cycles before, and this is the least recently used, then it's going to be replaced. The other one is the least frequently used policy. So these are the 2 well-known policies of least recently used and least frequently used. So your third project is going to be about running pretty much the same code that you have already and playing with the memory hierarchy. So one of the things that you can tune in Mars is what kind of replacement policy you want to have. And you're going to see how it's going to affect your performance. Okay, so you could do some kind of analysis to change the memory side. You use a fully associative cache, use a direct math cache. You change their placement policies, and you do a thorough analysis to see which one of this configurations of memory hierarchy is going to give you a better performance based on your application. Okay, so and that's going to be the last project, by the way. So now let's talk about the least recently used policy. Okay, so least recently used policy, as I said, it kind of goes backward in time and see which one is the least recently used. This values the temporal locality principle, as I mentioned. What we do in hardware for implementing such policy is we kind of create a counter. It doesn't have to be fluid counter, it can have different counter size. The bigger the counter is, the more information it can have, right? Also, there's a trade-off, overhead, counter, everything. So every time we access a specific location, we set the counter to 0. But with every memory access, we increment the counter anyways. So all the memory addresses, they have a counter. Every time that we have a memory access, no matter where it is, the counter is going to go up. But that specific location that we are caring about, we're going to get data from or store data to. For that specific location, the counter is going to be reset to 0. Okay? Every clock, no matter what, all the clocks increment the counter, except for the clock that we actually have memory access to. This is how we find the least recently used data. When the new data comes, when we have the capacity miss, that the full capacity cache is in full capacity, and when you need a new data, we just look at the counter. The one with the largest number is going to be replaced. Does that make sense? Okay, now let's see how it works. If I use the least recently used policy with this kind of memory address that I have here. So we have 0. We already know what happens with 0. It's the same memory. It has 1 bit per set, 3 bits per tag, same exact number, nothing is changing. So 0 is a compulsory miss, it's going to sit here, right? Then we have 4, the second compulsory miss, and then we're going to have 4 is set 0 as well. Now we have 0, and 0 is going to be hit, right? Now this is where the problem happens. Okay, this is where we have 12. 12 is pointing to the set 0. We look at the first bit. 12 is not there. Now we want to replace, and this is the capacity of the set is full. So we want to replace one of these blocks, one of these lines in the cache. Which one should we replace? What do you think? Okay, we have 2 answers there, that's right. Should I change? Who says I should change 0? How about 4? And some of you don't care, right? That's given an incorrect answer, it's fine. So one more time, who says it's 0? You have to choose one, you just can't choose nothing. You know, just have 2 options. 0, we have 1, 2. So it says we're going to change 4. Okay. So 4 is the correct answer, right? Why? Because we just accessed 0 in the clock before this, in the cycle before this. So the counter for 0 is reset to 0. But this one, I'm going to move 4. In this cycle, the counter is 1 up. So the counter is 1. But the counter for this is 0. So when I go to this, memory 0 has a smaller value. And I always replace the one that has a larger value. Okay, this is the replacement policy. We get rid of the 4 and replace that with 12. Now we have 12 here. The next value is 9. 9 is going to be a compulsory miss. I just put it here for you to see what's going to happen if you have a set 1. You can have a sense of that. So 9 is going to sit here because it's going to be set 1. Now we have 4 again. Okay. We have 4, and this is what I have in memory. 4 is going to be in set 0. Set 0 is in full capacity, so we have to replace one of them. Which one should be replaced? Who says 0 is the right answer? And who says 12 is the right answer? 0 is actually the right answer because 12 was accessed here, right? The counter was reset here at this point. The last time we had access to 0 was in this cycle. Okay, so this is least recently used. So it's a miss, and 0 is going to replace with 4. Then we have 0 here. Quickly, it's a miss. Which one should I replace? 12. Okay, new values here. This one's a hit. This is least recently used policy. This is how it works. Okay, so now let's talk about the least frequently used. It's pretty obvious, right? Least frequently used, we just count how many times we have access to that location. It still has a counter. Every time that we have an access to that location, the counter goes up. When we want to replace it, the address with the lower value in the counter is going to be replaced. This is the least frequently used policy. So now let's see how least frequently used work. We have the same kind of memory, same memory addresses. Okay? So let's see how it works. We have 0. I just changed memory addresses. It's not the same, sorry. So these two are replaced for the sake of the least frequently used. Okay. So we have the 0. The first one is a compulsory miss. 0 is going to sit here. We know how it works. The second one is, again, 0. It's a hit. And then we have 4. 4 is going to be a compulsory miss, and now we're going to have 4 instead 0 as well. Now we get to 12. Okay? So 12, we should replace, it's a miss. It's a capacity miss. It's not a conflict miss, by the way. So this is a capacity miss because we don't have enough capacity in set. Now we want to replace one of these addresses. Which one should we change? 0 or 4? 4. We should replace 4 because we had 2 accesses to 0 in the beginning, but we just have 1 access to 4. So this is a little bit messed up, right? Because we are not taking into account the temporal locality principle, right? But we just brought 4 in and we're getting rid of it. It's not necessarily a good thing. So it's not my favorite policy because if you have a loop in the beginning that keep using one memory address, you're going to keep that in the cache until the end, unless you kind of mix them. You have the least frequently used and the least, recently used combined together, and that's going to be something nice. So now we have 9. We know where 9 sits is a miss. Then we have 4. 4 is the new problem, but this is the problem with this least frequently used. Which one are we going to replace here? 12. Just because we have 2 memory accesses here, this is going to remain there, right? In some cases it works well, in some cases not. We have 2 weeks. Okay. So in this case, the hit rate increased a little bit because we had more zeros, but it's not necessarily the case. All right, so now let's talk about the last concept in this module. This is actually one of the things that we usually ask about in the qualifying exam, the comprehensive exam. So the cache performance is a topic that you can actually design interesting questions from. And it's actually a very important concept anyways, like in real world too. So we have, to calculate the cache performance, we have to go back to the concepts that we talked about in the second module, about the CPI, performance, and so on. And even in the final exam, when I ask design questions, we might not directly go back to the topics that we covered in the beginning of the class, but then directly through these types of questions, you need to know that information about the CPI, clock frequency, and everything, right? So, CPU time, we know that this is the clock cycles that the CPU expends in executing a program. Okay, that we know. Clock cycles multiplied by clock cycle time is going to give us the CPU time. Something that we didn't consider at the time was memory, right? So when we were calculating the CPI time, we didn't have this part. We're just saying that CPU execution clock cycle multiplied by clock cycle time gives us CPU time. But in reality, when you have a memory in the picture, this memory and stall clock cycles become important too. How many clock cycles you spend in the memory is gonna add to the CPU time. Okay? So how do you find the memory stall clock cycles? This is sum of all the clock cycles that we have to wait until memory gives us the data. It's kind of like average of that time. So how do you find this? So memory stall clock cycles is equal to memory accesses per program, because if you design a program that doesn't even need memory, then you don't even have this part. Okay, that's obvious. If you just work with registers, you don't have any memory access time. But now, the memory stall clock cycle time is the memory accesses per program multiplied by the miss rate of the memory multiplied by the miss penalty. Okay? If we have a memory access time and data doesn't exist in the memory and we have to go to the main memory and bring it, that's the miss penalty. So we have to multiply the miss penalty by miss rate and multiply that by the memory access per program, and that gives me the memory stall clock cycles. This can be rewritten in terms of instructions. So we have how many instructions we have per program and how many misses we have per instruction multiplied by the miss penalty. Okay? So now let's have some examples here. So we have a processor that has a CPI of 2 and is running a program that has 36% load and store instructions. Okay. But 36% of your instructions is memory access instructions. So if the instruction cache and data cache has a miss rate of 2% and 4%, and the miss penalty is 100 cycle for all misses, no matter if it's a data cache miss or instruction cache miss. We have 100 cycles for miss penalty. So we want to see how much faster the processor would be if we had a perfect cache that never missed. Okay. Alright, so now let's solve this. So CPU time, from the equation that we had in the previous slide, is CPU execution clock cycles multiplied by clock cycle time, right? And the memory stall clock cycles is instructions per program multiplied by misses per instruction multiplied by miss penalty. Okay. So now, if we have a perfect processor that never misses, it means that the miss rate is 0, right? We already had this equation that the miss rate is 0. If the miss rate is 0, then we can ignore this memory stall clock cycles, and we can have instructions multiplied by CPI is going to give me the number of clock cycles that I have in CPU for executing that program, right? So it's going to be 2 multiplied by the total number of instructions. Now, let's see what the memory stall clock cycles is, considering that cache information that we had. We had a 2% miss rate for the instruction, and 4% miss rate for the data, and miss penalty of 100 cycles. Okay, so memory stall clock cycles is equal to the instruction miss cycles and the data miss cycles. So we had to add them. Okay, so instruction miss cycles, we know that we have a 2% miss rate and a miss penalty of 100 cycles for both cases. So it would be instructions multiplied by 2% multiplied by 100. For the data miss cycle though, we have to check what's the percentage of the load and store instructions. Because for the instruction memory, every instruction should go to the instruction memory, no matter what. 100% of instructions go to the instruction memory. For the data memory, only the percentage of the load store instructions go to the data memory. Okay, so when you have 36% here, we have to add this 0.36 multiplied by instruction, because that's how many instructions we sent to the memory, multiplied by the miss rate for the data cache, which is 4% here, multiplied by the miss penalty, which is 100. Now, if we do the math here, we're going to get 3.44 instructions. Okay? So 3.44 instructions here. and we have two instructions, 2 times instruction for the CPU execution clock cycles. Now, if you want to calculate the CPU time, we need to just add the CPU execution clock cycle from this relation here with the memory installed clock cycles, which is 2 times instructions plus 3.44 times instructions multiplied by clock cycle time. This is going to give me 5.44 times instructions clock cycle time. This is the case with the memory that has those miss rates. If we have a perfect memory, if you have a perfect system that doesn't have any miss rate is equal to 0, we would have gotten the 2 times instruction for this. So now, to find the speed up, you just have to divide these two. Right? We have the CPU time for the case that has memory misses, and then we have the CPU time for the perfect case. If we just divide them, we're going to get the speed up of a perfect cache, which would be 2.72. Does that make sense? Okay, so now let's have another question. So we have a processor with a base CPI of 1 and a clock rate of 4 gigahertz. Okay, and then we have a main memory access time of 100 nanoseconds, including all the mishandling. And we have a 2% miss rate per instruction at the primary cache. Okay, 2% miss rate for each instruction. So what is effective CPI? To find effective CPI, we have to follow this equation, which is basically common sense. If you work on the previous equation, you can get there. But you can just have this in mind. Effective CPI is equal to base CPI plus memory install cycles per instruction. So we kind of find the average of memory installed cycles per instruction and add it with the base CPI. That's going to give me the effective CPI. Okay. So now we already have the information about the base CPI, which is equal to 1. That we already know. Now we have to find the memory installed cycles per instruction. This we already know that follows this relation of miss rate multiplied by miss penalty. Okay, so miss rate, if you know the miss rate, and if you know the miss penalty, we can calculate the average memory install cycles per instruction. Now the miss rate we know is equal to 2% here, but now we have to find the miss penalty. Because we're working, so this is the part that a lot of people make mistakes. You have to make sure that you're working with the same units, right? Sometimes I provide the information in seconds, but the question I'm asking is in clocks. So when we talk about the CPI, we're talking about the clock per instruction, right? So if you want to find the miss penalty and everything, you have to convert everything to clock cycles before doing it. So now we know that the memory access time is 100 nanoseconds. But how many clocks is this? That's the thing that we care about, because we are finding the effective CPI, which is clock per instruction. So the first thing I do is finding the cache miss penalty in terms of the clocks that it consumes, right? So I have the clock cycle time of clock rate of 4 gigahertz, which means that the clock cycle time which would be 0.25 nanoseconds. 1 divided by 4 gigahertz. That's how you need to use whatever we talked about in module 2 to answer this question. Okay, so 1 divided by 4 gigahertz is going to give me 0.25 nanoseconds. Now the cache miss penalty is 100 nanoseconds. If I divide that by 0.25 nanoseconds, I'm going to get 400 clocks. So miss penalty is 400 clocks. That is the information I can use to calculate the CPI here. So now I have the miss penalty of 400 clocks, and I have a miss rate of 2%, 0.02. If I multiply these two and add it with the base CPI, I'm going to get the effective CPI of 9. Is that clear? So the tricky part here wasn't these calculations, was the fact that you only see 100 nanoseconds, you have to convert it to clocks because we're working with CPI. So now the second part of the question. So how much faster will the processor be if we add the secondary cache, so now we are adding a second layer of the cache, that was just one layer, that has a 5 nanosecond access time and is large enough to reduce the miss rate to main memory to 0.5%. So it means that the second layer cache has a miss rate of 0.5% and a miss penalty of 5 nanoseconds. That's how you should interpret that. If you do it, then it's easy. After this point, it's just going to be an addition to whatever we had. So miss penalty for this one is 5 nanosecond, miss rate for this one, which is second layer cache, is 0.5%. Now, if I want to find the speed up, we have to find the effective CPI. That would be enough. If you find the effective CPI, that's enough because the same clock frequency for both systems, and it's the same number of instructions for both systems. So we just find the CPI, and that is enough for finding the speed up. So now, to find the speed up, we get the effective CPI of the system with 1 layer cache and divided by effective CPI for a system with 2 layer cache. Okay? So, L1 cache miss penalty is 5 nanoseconds divided by 0.25 nanoseconds. But that has changed now. So when we had 1 layer, the main memory access time was 100 nanoseconds. When we added the second layer of the cache, it reduced the access time to 5 nanoseconds. So now it means that the miss penalty for the first layer of the cache is 5 nanoseconds. But the miss penalty for the second layer is going to still be 100 nanoseconds because you have to go to main memory anyways. Now for the second layer, you have to go to main memory. And we know that this main memory access time is 100 nanoseconds. So going back to this, the miss penalty for layer 1 is reduced to 5 nanoseconds. If I convert it to clocks, it means that I need 20 clocks for the miss penalty of layer 1. For the miss penalty of layer 2, we have to find the main memory access time, which gives me 400 clock cycles again. Right? So now I have the first layer cache miss penalty and the second layer cache miss penalty. I also happen to have the information about the miss rates of each layer. The 2% hasn't changed from the partial credit 1, and I know that this is 0.5% for the cache layer 2. So if I want to find the effective CPI, I have the base CPI here. Clock cycles installed in the first layer cache would be 0.02 because of the 2% miss rate multiplied by the 20 clock cycles, which is the new miss penalty, plus 0.005, which is this 0.5% miss rate for the cache layer 2, times by 400, which is the miss penalty for the cache layer 2. So if I add these guys, I will get 3.4. So now you can see how adding a second layer cache could change the effective CPI from 9 to 3.4. If I want to calculate the speed up, I divide 9 by 3.4, and it gives me a 2.6 speed up. Does that make sense? So now everything we discussed so far was excluding one parameter, and that was hit time. Okay. In all these assumptions, everything we talked about so far, we assume that there's no time spent on bringing data to processor. We're just looking at the miss penalty and miss rate. Okay. But how about the hit time? Every time that we want to have access to the memory, it takes some time for the memory to bring the data to processor, right? So for that, we have a concept, a term called average memory access time, or AMAT. And AMAT is pretty much the same thing that we talked about until this point, but it also includes the hit time. So AMAT, this part you're familiar with, the miss rate multiplied by miss penalty. But here we also add the time for a hit, or clocks for a hit, right? Depending on how we want to do the calculation. So the important thing with AMAT is, with previous example, we kind of understood it. I can design questions in a way that has many layers, right? Something that you have to keep in mind is that the AMAT for layer 3 is the miss penalty of layer 2. So average memory access time for layer 3 is the miss penalty of layer 2. Average memory access time for layer 2 is the miss penalty of layer 1, right? So what you do when I give you this question, you start from the very last layer. You calculate the AMAT for the very last layer, and that gives you the miss penalty of the second layer. And you keep doing this until you find the actual CPI or CPU time. Okay, you always start from the last layer. So now let's have this example. We have a processor with a 1 nanosecond clock cycle time and a miss penalty of 20 clock cycles, a miss rate of 0.005, this is per instruction, and a cache access time of 1 clock cycle. That's the new information that we didn't have before. Yeah, the cache access time of 1 clock cycle. So assuming that the read and write miss penalties are the same and ignoring the other write stalls, find the AMAT for this processor. Okay. So what was AMAT? AMAT was time for a hit plus miss rate times miss penalty. Again, something you need to keep in mind is that you want to calculate the AMAT in terms of clocks or in terms of seconds. You can do both. You can actually calculate AMAT all the way in terms of second at the very end of the conversion to the clocks, or you can convert everything to clocks in the beginning and then go ahead with that. Usually it's the clocks that we care about because we ask about the base, effective CPI and so on. But now let's see, this is one way of solving this problem. Obviously you can solve a different way too. So time for a hit is cache access time. Cache access time, if you look at it here, it says 1 clock cycle. 1 clock cycle is also 1 nanosecond. If I want to solve this in terms of seconds, like it's 1 nanosecond. Now the miss rate is 0.005 and the miss penalty is 20 clock cycles. The miss penalty of 20 clock cycles is also equal to 20 nanoseconds because of this clock cycle time that I have. So now if I want to calculate AMAT in terms of seconds, I'm going to get the 1 nanosecond for the hit rate plus 0.05 multiplied by 20 nanoseconds, which would be 2 nanoseconds, or 2 clock cycles. Another way of solving this problem was converting everything to clock cycles in the beginning and don't do any conversion at the end. Okay, so this is where I want to stop.